Hello Professor, this is assignment 7.3 and problem 7.3.5. In this problem, um, this is a question like minimizing x plus y subject to x plus y greater than equal to 6, 3x minus y greater than equal to 9, and xy greater than equal to 0. The objective function is to minimizing x equal x plus y subject to x plus y greater than equal to 6, 3x minus y greater than equal to 9, x greater than equal to 0, and y greater than equal to 0. Now we converting each of the first inequality to equation by subtracting new non-negative surplus variable y1 and y2. Either of the surplus variable is negative, the constraint is not satisfied. Minimizing x equals y plus y, x plus y subject to x plus y minus y1 equals 6, 3x minus y minus y2 equals 9, x greater than equal to 0, y greater than equal to 0, y1 greater than equal to 0, and y2 greater than equal to 0. This is a graphical figure about this is a geometrically graphics, and this represent x, y, y1 and y2 variable. This is a figure, and now we are solving the equation, and for the second intersection point we assign the variable x and y1, set them to 0, resulting in the system x equal y minus y2 equals 9. That's a solution. And y equals 6, y2 equals minus 15. The second constraint is variable by 2 equals minus 15, indicating the iteration point infeasible, 0 and 6. Now for the third iteration we set x and y2 and set them to 0, resulting in the result x minus y1 equals to 6, y minus equals to 9. That is the solution. And y equals minus 9, y1 equals minus 15. So the constraint is validity by the y equals minus 9, indicating the iteration point infeasible, 0 minus 9. And now we will solve the entire problem, and then we will in the summary of the 6 possible iteration we found 4 interaction to be feasible. For the 4 we find the value of objective function by mere substitution. The objective function at the extreme point is evaluated as the follow: a equals 6.0 and b equals 3.75 and 2.25, and we will get this type of table. Let's understand by using the code. This is the code that we are going to use to solve this problem. When we run the code, I don't know why the code is not running, but now it's running. Okay. In this problem we are trying to find the algebraic solution. The objective of the assignment is to minimizing x equals y, x plus y subject to x plus y greater than equal to 6, 3x minus y greater than equal to 9, when x greater than equal to 0 and y is also greater than equal to 0. we will create a two-dimensional array and concatenated them. First of all, we create two-dimensional array and concatenated them two arrays, and then we will get the number of columns and number of rows of the concatenated array. Then we will create another array to calculate the calculate all possible combination that we would need to run the linear equation on. In output section, we can see all possible combination of 1, 2, 3 and 4. 4 in two-dimensional array. Then we will create another array to store the result that we would get after applying the linear equation. Then we calculate two additional array that would be used later in the code. Now we will run the loop on all possible combinations and apply linear equation on each of them and store the result in the result array. Now we will see in the output that we have result after applying the linear equation on possible combination. Now we take the first two column. And store them in a new array called results1 that would be used later in the code. Then we will create two additional array. One would store the feasibility of result and another one would store the objective value. Now we will run another loop that would run together all the rows and results1 array. Feasibility is basically to confirming if all the values in the particular row is greater than equal to 0. And you can see in the output that 0, the row 1, 2 and 4, 5 are not feasible because at least one value is less than 0. Now we will calculate the objective. The objective is now to just put x and y value and add them together. Once we run this loop, we get all over objective calculated, as you can see in the output. You can see in the output we get the concatenated table as well. So, if we look at the feasible intersection point, the maximum value is 6. You can see over the 6 intersection points, only 2 are feasible, and since the objective is to minimize an increasing function and the optimal value lies in the level curve x plus y equals 6. The segment formatted by two feasible intersections 0, 6 and 3.75 and 2.25 respectively coincides with the level curve x plus y equals 6. Each point between 0, 6 and 3.75 and 2.25 as well as the stream point themselves is an optimal solution. Thank you.